Imagine your team ships a bad release. It breaks Redis timeout handling, and errors spike across the order service. Someone catches it fast. Rollback lands within 10 minutes. But the backend doesn't recover. It stays down for another 50 minutes. CPU pinned near 100% across every service downstream, after the bug that caused it is already gone. How does that happen? That's not a rollback failure. That's a retry storm. Here's the thing. The bug wasn't what kept that system down. The retries were. Every client that got an error during the outage kept retrying politely, exactly as designed. And thousands of polite retries, all landing on a service that was already on its knees. That's what actually took it down. Retries are supposed to make systems more reliable, but get the policy wrong, and they become the outage. Same failure shape, whether it's a microservice or an agent's tool calling loop. The only difference is whether the bill shows up in CPU or in token. By the end of this, you'll know why removing the cause doesn't end the failure, and the 3 specific controls that would have stopped that 50-minute tail cold. So, 4 things. Why retries synchronize into storms, why the failure outlives its trigger, what the agent version of this costs you, and the fix that actually holds. Let's start with the simple version. 100 clients call a service, and it has a bad second. Errors all 100 of them at once. Naive retry. Wait 1 second, try again. But all 100 retry at the exact same moment. If the service is still recovering, it errors all 100 again. Now, they're synchronized on a 2-second retry. Then 4. The retries never spread out. They just get bigger and further apart, like a pulse. AUS actually ran this experiment with no randomization. Retry traffic clusters into visible spikes. They measured synchronized peaks recurring every 32 seconds in a real serverless system. Add jitter, randomize the weight instead of fixing it, and at 100 competing clients, total call volume dropped by more than half. Same clients, same failure. Half the load because the retries stopped arriving in lockstep. So, that's step 1. A retry policy without randomization isn't smoothing recovery. It's scheduling a stampede. But jitter alone doesn't explain the Yandex incident. That system had backoff, and it still stayed down for 50 extra minutes. Here's the part that's counterintuitive if you haven't hit it. Once retry traffic passes a threshold, the system can get stuck in a failure state that sustains itself. The trigger, the bad release, is gone within 10 minutes. But the retries it generated are still arriving, faster than the recovering service can drain them. Every retry that times out generates another retry, and the queue doesn't shrink. It's not that the fix didn't work, it's that the fix and the ongoing damage are now 2 separate problems. Distributed systems researchers have a name for this. Metastable failure. Vulnerable state, plus a trigger, plus a self-sustaining effect, usually retries, that outlives the trigger itself. And it's been independently rediscovered often enough that practitioners have 3 or 4 names for the same thing. Retry storm, death spiral, persistent congestion. So what did Yandex actually ship? Not add more backoff. A retry budget cap retries at 10% of the successful request rate, enforced locally per client, no coordination needed. Once the budget's spent, a client stops retrying and fails fast instead. They reported 0 retry amplification incidents in the year after. Now, here's the part that's easy to miss if you're building agents instead of microservices. This is the exact same failure, just built differently. An agent's tool calling loop with no hard iteration cap, And no loop detection behaves exactly like an unjittered retry client. It hits a failing tool, retries, gets a similar failure, retries again, and because each attempt resends the accumulated context, the cost isn't linear. One reported case: roughly 50 times the token spent after 10 correction cycles on a single task. Same mechanism as the CPU spike, just a different meter. And the tell is the same too. Nothing looks broken from the outside. No crash, no alert, just a quietly enormous bill, and a task that still isn't done. So here's what actually holds. And it's 3 controls, not 1. Cut any of them, and the failure reopens. First, classify before you retry. Was this a network failure, where nothing landed on the other side, safe to retry? Or could the write have already happened, where retrying risks doing it twice? Stripe's idempotency key pattern is the clean version of this. Tag the request with a key. The server stores the result of the first attempt and replays it on repeats instead of re-executing. That turns, is this safe to retry, from a guess into a lookup. Second, back off with jitter. Always, on every retry, the AWS numbers from earlier, non-negotiable and cheap. Third, the one Yandex was missing, a circuit breaker with a budget. Once error rate crosses a threshold, the breaker trips open. Stop sending traffic to the struggling dependency entirely. Fail fast. Run an explicit fallback. After a cooldown, let exactly one trial request through, half open, and only close the breaker again if that succeeds. No unbounded retry queue ever gets the chance to build up, because past the threshold, nothing retries at all. That's the fix that held for a year. Not smarter retries. Retries with a ceiling. If you're shipping this Monday, cheapest first. 1. Add jitter to every retry you already have. It's a few lines, and alone it cuts synchronized load by half. 2. Put a hard cap on retries as a percentage of traffic, not an absolute count. 10% is Yandex's number. Tune it, but have a number. 3. Wrap anything that can cascade in a circuit breaker with a real fallback path, not just a longer timeout. And if you're building agents specifically, the tool calling loop needs the same cap, a max iteration limit, and a check for, have I seen this exact failure before? Costs you almost nothing. And it stops the 50 times token spend version of this same story. All of this assumes each retry has a fixed chance of failing. Next time, why even a 95% success rate per step still means most of your long agent runs fail, and the actual arithmetic behind it.